12.2. So last time we ended by talking about limits of vector valued functions. Now we're going to move up to differentiating and integrating vector valued functions. And the main idea stays pretty much the same because, derivatives and integrals are limits. So basically that idea was whenever I do any of these calculus operations on a vector valued function, I do that by just doing it to each individual component separately. So if I want to find r prime of t, find the derivative of a vector valued function, I know that it's just going to be the derivative, or it's going to be a vector valued function whose components are just the derivative of these components. So derivative of t is 1. So 1i, just I. Derivative of t squared plus 2 is going to be 2t plus 0, so 2t plus 2tj. And that's the derivative. Another differentiation example. So now we have a different vector valued function, this time in 3 dimensions. And same idea. If I take the derivative of cosine of t, I get negative sine of t. So that's the I, or the x component of the derivative. If I take the derivative of sine of t, I get cosine of t. So cosine of tj. And then derivative of 2t, I get 2k. And that's my answer. That's part A. Now for part B, we want to find the second derivative, which we can do in the exact same way. So derivative of negative sine of t, we would get negative cosine of t. That will be my I component. Derivative of cosine t, we get negative sine of t. That's my j component. And derivative of 2 is 0. So my k component would be 0k, which I'm not going to write. And there we go. Now, if I look at part C, it wants us to take the dot product of the first two derivatives. And general rule here, when we do vector operations with these derivatives, you kind of have to just look at how things are written, right? Pay attention to notation and carry out the operations with that in mind. So the idea here is I'm taking these derivatives first, and then I'm taking the dot product. Since I already know what the derivatives are, I can just use my component times component definition of dot product to get the answer. So r prime of t dot r double prime of t. All right, we multiply negative sine t times negative cosine t, we get positive sine t cosine t. Keep in mind there is no vector component here because when we did this with just number components, the answer ended up being a scalar. So in that same kind of train of thought, whenever we take the dot product of two vector valued functions, the result is just a regular function, not a vector valued function. So with that said, uh, plus, then we multiply cosine of t times negative sine of t, which is going to end up giving us minus sine of t cosine of t. Okay, and then multiply my z components together, I get 2 times 0. So that's just 0. And then if I combine these together, I end up just getting 0. So the dot product is 0. Remember, what does that mean? It means that r prime of t and r double prime of t are orthogonal. All right, D. So this time we want to take the cross product between the first derivative and second derivative. And again, I'm going to mention when you're doing these vector value or these vector operations, take your derivatives first and then do the vector thing, right? It all depends on how it's written. You'll see what I mean by that in the next example. So I already know what these two are. All I have to do is set up my cross product. So that's going to be the determinant of this matrix. Second row will have the components for r prime. So that's negative sine t, positive cosine t, and 2. Then third row, we're going to put the components for r double prime. So that'll be negative cosine of t, negative sine of t, and 0. And other thing I want to point out, remember when we had just vectors with constants as the components, the cross product was another vector. So if I take the cross product of two vector valued functions, the result will also be a vector valued function. So note the difference between those two. When I did the dot product, I ended up getting just a function of t, not vector valued. When I take the cross product, I will end up getting a vector valued function with t as the parameter. So working this one out, we can take the same approach that we did with just regular numbers, right? So remember, you block out the first row and each column one by one. So if I block out the first column, then this is the 2 by 2 matrix I have. So we get I times this determinant minus j times this determinant two zero. Okay. And then plus k times this determinant. Okay. Now going through, remember how these 2 by 2 determinants work. Just multiply the diagonal minus multiply this diagonal. So cosine of t times 0, that's going to give me 0, minus negative 2 sine t gives me just 2 sine of t. And that's going to be the x component. Now for this one, same thing. Sine of t negative times 0 gives me 0, minus negative 2 cosine t gives me 2 cosine t, but remember we have this negative there. So this is my j component. And then for the k component, negative sine of t times itself gives me sine squared t minus negative cosine squared t. So minus a negative we add. And here comes that trig identity again. We know that that's 1. So our answer is going to be 2 sine of t I minus 2 cosine of t j plus k. And there we go. We have another vector valued function. Moving on to the next example. All right, we're finding derivatives still, but this is what I meant by look at the notation. So before we were taking derivatives and then taking the dot product or the cross product. Here, because of this notation, I'm taking the derivative of the dot product, derivative of the cross product. So I would need to do my vector operations first and then um, take the derivative. So first thing, let's look at part A. Now you might be thinking, well, I thought that dot product gave us a number and the derivative of a number is zero. So shouldn't that be zero? No. Remember, when we take the dot product of two vector valued functions, it doesn't give us a constant. It gives us a function that is not vector valued. So the result of this is just going to be some function of t. There's not going to be an I, j, or k in it. Right? And then when I could take the derivative of that just like I would if I were a Cal 1 student. With this one, though, we take the cross product. Remember, that's going to give us a vector valued function. Then we have to differentiate the vector valued function. So our final answer will have I, j, and k in it. So that's the difference between those two and kind of logical faux pas that some of you may have assumed going into this. Okay, so first, for part A, I'm going to start by figuring out what the dot product is. So R of t dot U of t. Okay, we can multiply the components together. So if I take 1 over t multiplied by t squared, okay, I'll get my I component. Well, not a component. I get the result from the I component plus -1 times -2t plus natural log of t multiplied by 1. So the result that I get, this is going to end up giving me t. This is going to give me 2t. And this is going to give me the natural log of t. So I end up getting 3t plus the natural log of t. So that is the dot product of r and u. Now, if I want to take the derivative of r of t dot u of t, I'm really just taking the derivative of this guy, 3t plus natural log t. So it basically reduces itself to a calculus 1 problem, right? Derivative of 3t, we get 3. Derivative of natural log of t, we get 1 over t. And that's the answer to part A. Now for part B, we have to start by getting the cross product between u and u prime. So out to the side here, I'm going to write out what u prime of t is. Right? Derivative of this first component, we get 2t, so 2ti. Derivative of my second component, I get -2, so minus 2j. And then derivative of 1 is 0, so there is no k component for this one. Now that we know what u prime looks like, we can write out our determinant. So we're starting off by getting u of t cross u prime of t. So taking our determinant, first row is our unit vectors I, j, k. Second row will have components of u of t. So that'll be t squared minus 2t and 1. And then third row, we get the components of u prime of t. So we get 2t, -2, and 0. And then it works just like the last cross product that we did. right? So if I eliminate first column, first row, I end up getting I times this determinant minus j. Now, if I eliminate the second column, first row, we get this determinant plus k. And if I eliminate the third column, we're left with this determinant. Okay. So if I take these 2 by 2 determinants, I end up getting 0 minus -2. So 2i, 0 minus 2t, but there's already a negative here. So plus 2tj. And then for this one, we get -2t squared minus -4t squared, right? So that's going to end up giving me, what is it? -2t squared minus a negative, so plus 4t squared. Yeah. So I end up with plus 2t squared k. Okay, so now that we've got the cross product, to get the final answer, I need to differentiate my cross product. So I'm taking the derivative of 2i plus 2tj plus 2t squared k. The result, remember, is going to also be a vector valued function. We just have to take the derivative of each of these components separately. So derivative of 2, we get 0, meaning our final answer will not have an I component. Uh, Derivative of 2t, we get 2, so 2j. Derivative of 2t squared, we get 4t k. And that is our final answer. Now let's move on to some integrals. Oh, that printed funky. So this is an integral sign. Hopefully the PDFs look right. Okay, so we want to find the indefinite integral of this vector valued function. So this is going to work the same way that derivatives did. We're just going to take the integral of each of these components separately, and that's going to be the answer. Now, one question you might have is what about the plus c? I remember if we do an indefinite integral, we have to write the plus c. Thing is, you're going to have a plus c for each component. So we'll call one of them C1, the other one C2. You could call them CI, CJ, whatever. The point is that we have separate constants, separate c's for each component in our vector valued function, right? It wouldn't make sense for me to just have a c at the end of this because then it's not really a vector, it's some weird concoction that doesn't really apply to anything. I don't know. But anyway, moving on. We're just going to take the antiderivative for each of these terms. So remember, for this one, we add 1 to the power, divide by the new power. So for my I component, I'm going to have t squared over 2 plus c1. That's going to be my I component, parentheses, very important here, because when you're adding that plus c, you have more than one term in that component. So you do need to put it in parentheses. All right, derivative or antiderivative of 3 would be 3t. So plus 3t plus c2j. And that's my antiderivative. Now looking at the next one, we'll do a definite integral. So remember how these work. First, you have to get your antiderivative, and then you're plugging in values for t. So first thing, this root t, or the cube root of t. Remember, when we have roots like this, we typically are going to write them as powers. So this would be t to the 1/3, not -3. Remember, -3 would put it in the bottom. Yeah. But t to the 1/3, and we can do our power rule for integrals with that. For this one, this is very similar to 1 over t. So the antiderivative would be a natural log. Remember, though, that if you have a coefficient for this t, you would technically need to do u sub, and that's going to introduce a constant in front of the natural log. And then e's. So remember with e to a power, it's just e to that exact same power divided by the coefficient. That's it. So without further ado, I know that for the I component, I'm going to add 1 to the power. So that'll be t to the 4/3, leave a little space. And we're dividing by 4/3. Remember, if you divide by a fraction, that's the same as multiplying by its reciprocal. So divide by 4/3, that's the same as multiplying by 3/4. So this is going to be my I component. I'm not going to write a plus c though, because this is definite, and we have to plug the bounds from our integral in. So I don't write a plus c for this one. Now I mentioned here that the antiderivative is going to be the natural log. Remember, when you go backwards, it's natural log of the absolute value of the bottom. Okay. And then j, and then negative e to the negative t k. And we're going to evaluate that from t equals 0 to t equals 1. So the way that works is we plug in the top number first to everything, plug in the bottom number, and subtract. So altogether, if I plug 1 in for t, 1 to the 4/3 is 1, times 3/4 gives me 3/4 I. Okay, natural log of 1 plus 1, that's going to be natural log of 2j. And then e to the negative 1, that's just 1 over e. So minus 1 over e k. Okay, this is what I get from plugging in the top number. From that, I'm going to subtract what I get from plugging in the bottom number, 0. So 0 to the 4/3 is 0, times 3/4 gives me 0. 0 plus 1, I get 1. Natural log of 1, you guessed it, is 0. E to the 0 is not 0, it's 1. So minus k. And basically, you have to remember now that if I add or subtract vectors, that only applies component-wise. So 3/4 minus 0, I get 3/4 I. Natural log of 2 minus 0, I get natural log of 2, j. And then 1 minus, or negative 1 minus, no, minus, negative 1 over e minus negative 1 gives me 1 minus 1 over e k. And that's my answer. One more example for you. We want to find the antiderivative of this vector valued function that satisfies this initial condition. Yeah. So start off by just taking our integral. So I want to take the indefinite integral of r prime of t with respect to t. So for the first one, we have cosine of 2t. Remember, when you have a coefficient in front of this argument, or in front of this t, then technically we're doing a u sub. Just to remind you, because it may have been a while since you did one. For this one, I would let u be equal to 2t. That means that du is equal to 2 dt. Right, we just differentiated each side. So I can replace, so if I'm doing an integral, I might as well just write this out here. remember we can replace our 2t with just u, right? I don't have a 2 dt though, I just have a dt. So what I can do is I can divide both sides by 2 or multiply both sides by a half. So I end up getting 1/2 du is equal to dt. And of course, this is I. Yep. So when I take the antiderivative, I can actually make all of these substitutions, replace the 2t with u. I can replace dt with half du. But since 1/2 is a multiplying constant, I can just take it out front of the integral. So essentially, this antiderivative is going to give us the same thing that this one would. And now I'm just taking the antiderivative of cosine of u, which would be positive sine of u. Remember, when you're integrating, the negatives are opposite of what they are when you take the derivative. So positive 1/2 sine of u, right? But remember, we don't want to keep it as u. We want to put the original thing back in. Okay, and there we go. We got the I part. I'm not going to go through this for the others. Actually, I don't have to go through that for the others because they don't have coefficients. Right? This one has a coefficient, but it's out all the way in the front. So it's not the same as with this guy. So -2 integral sine of t dt for our j component and the integral of 1 over 1 plus t squared dt for the k component. Right? And because I am a stickler for notation, I'm just going to copy pasta this here. And then actually evaluate them in this last step. Okay. Antiderivative for sine of t would be negative cosine of t. Again, when you're integrating, the negative things are backwards. So since there's already a minus there, that'll become plus 2 cosine t plus c2. Need my parentheses. J. And then this is a form that hopefully you still recognize. That is the derivative of arctangent. So the integral of this guy would just be arctangent, which I'll write as tangent inverse to save space, of t plus c3k. All right. So now we have our antiderivative. We need to go back and look at our initial condition. So we know that r of 0 is going to be whatever we get substituting 0 anywhere that we see t in this antiderivative. So I'm going to get 1/2 sine of 2 times 0, which is 0, plus c1 I, plus 2 cosine of 0 plus c2, that's my j, plus arctangent or inverse tangent of 0 plus c3k. Now, for each of these, you can kind of treat them all as their own equation. We know that this vector has to be equivalent to what we've written or what we were given up here. That tells me that my I component, right, 1/2 sine of 0 plus c1 has to be equal to 3. My j component, 2 cosine 0 plus c2, has to be equal to -2. And my k component, arctangent of 0 plus c3, has to be equal to 1. So if I solve these equations, first, sine of 0 is 0, so I'm automatically going to know that c1 is 3. Cosine of 0 is 1, so I know 2 plus c2 is equal to -2, which means that c2 is -4. Lastly, arctangent. Remember how this one works. You have to figure out what angle gives me a tangent of 0. And the answer to that would be 0 radians. Because remember, tangent is sine over cosine. So if tangent is equal to 0, then sine is also equal to 0, which will happen at 0. So this ends up just being C3 equals 1. Now that I know what the values are for my constants, I can give my final answer. I know that R of t is going to be 1/2 sine of 2t plus 3. That's my I component. Plus 2 cosine t minus 4. That's my j component. Plus arctangent of t plus 1. And that's my k component. And this is my final answer. And that wraps up section 12.2. Remember, your big idea here is to take derivatives and integrals of vector valued functions. You just do the derivatives or integrals to the individual components. Additionally, whenever you have questions that combine vector operations or really any kind of operation with differentiating or integrating, look at the notation, make sure you do things in the correct order. All right, and with that, I bid you adieu. Happy mathing.